There are two standard one-dimensional heat transfer geometries. The first is 1D rectangular, and I've already done a YouTube video on how to solve the simplest steady 1D rectangular heat transfer problem. And so this video is on the second standard condition, which is 1D radial. So the problem I'm addressing is, what is the steady state temperature profile in a long cylindrical shell if the inner wall is held at T1 and the outer wall is held at T2, which is a lower temperature? And also, what is the heat flux in the shell? So as was true with the 1D heat conduction in a rectangular solid, we're going to solve it with the microscopic energy balance. Whenever we're asked a question about the temperature profile, so what is the temperature profile? That means we have to do a microscopic balance, because the microscopic balance zooms in into tiny regions in space inside the domain, and tells us about how the temperature varies with position. So our domain here is between R1 and R2. So R is between R1 and R2, and that's the region over which we're solving for the temperature profile. So the microscopic energy balance is given by this equation. I'm going to have a more zoomed in version in a second. If you'd like a copy, it's available online. And my handout has a version that's written in terms of the flux on the front, and a version that's written in terms of the temperature profile, the temperature as a function of position and time on the back. It also has the Fouriers Law of heat conduction, which we'll need in order to assess the flux. And we'll talk about that in this problem. So here's the problem statement again. And I have a zoomed up version of the microscopic energy balance that we can then use to find the differential equation that we need to solve. So it asks for the steady state temperature profile, and that's addressed here in the temperature as a function of time. If it's a steady problem, the temperature doesn't change with time. The next grouping of expressions in the microscopic energy balance are related to the convection of energy into the microscopic control volume. And that means that it asks questions about the velocity field. So the domain that we're working on is between R1 and R2, and it's the solid shell. And there's no flow whatsoever inside a solid shell of, let's say, steel. And so these three velocity components are zero. On the right-hand side of the microscopic energy balance, there's the thermal conduction terms. They all have the conductivity out front. And it asks questions about how we expect the temperature profile to vary with position. And this first grouping asks, do we expect the temperature to vary in the R direction? And my favorite way to convince myself without a doubt whether or not there's a variation in the direction is to identify two locations, let's say R1 and R2, and ask myself, are the temperatures different? So in this case, we were given that the temperature at R1 is T1 and the temperature at R2 is T2. So they are different. So certainly we do expect the temperature to vary when R is different. And so we keep this term. The next term is the second derivative with respect to theta. And it's asking if we expect there to be a variation at different theta positions in the tube. And we don't expect that. So we can call that theta symmetry and say there should be no variation due to theta symmetry. The final term asks about variation in the z direction. So the z direction would be going down the tube direction. And when we have a very long tube, there would be something interesting happening at the inlet and the outlet, perhaps, because it gets complicated and we're not exactly sure what this device looks like. But if the tube is really long, then any effects of the ends are negligible. So that's a classic, again, entry 1D assumption is that for a very long tube, there would be no variation in the z direction. And the final expression is related to the source term. So I've put here at the top of the sheet the typical types of places where there might be a source of heat. There might be viscous dissipation. If there were a velocity, there could be viscous dissipation. So there's no non-zero velocity. So that one's not producing extra heat. There could be electrical energy. So the question is there any electrical current flowing in the domain that we're asking for? And there isn't. It's just a tube. So there isn't any electrical energy. And the third is asking about chemical energy, again, in the domain where we're solving the problem. Is there exothermic or endothermic chemical reaction? And there isn't, no reaction. So those are the reasons. Sometimes I don't even ask myself about viscous dissipation because that's pretty rare. But the two common ones would be electric current and chemical reaction, and they're not there. And so this one is 0 because there's no electrical current and no reaction. So we have simplified the governing equation as much as we can, and now it's time to solve. So I'll copy this resulting equation onto the next sheet. So what we have is 0 equals k over rho Cp times 1 over r d by dr of r dt dr. So those are what we are resolving. There's a 0 on the left, and the rest is as copied. So now we can solve this, and we're going to note that because the temperature is not a function of theta or z, we don't have to use the partial derivative notation anymore. So I'm going to change the partials to total derivatives. And then I'm also going to divide both sides by k, and so it drops out. Multiply both sides by rho Cp, and so they drop out. And then multiply both sides by little r, and everything there drops out. So I end up with d by dr of r dt dr equals 0. Now, sometimes people are tempted to take a derivative here, but remember, we're integrating. So don't differentiate while you're integrating if you can help it. So I'm just going to call this phi. And so now I have d phi dr is 0. And that one I'm certain I know how to integrate. So when I integrate a function, I get 0 plus a constant. And so phi is equal to a constant. But phi, of course, is just r dt dr, because that's what we defined it to be. And now I'll solve for dt dr. So dt dr is equal to c1 over r. And that's another integral that I know how to do. So this is the integral of 1 over r is just natural log of r. So I get t equals c1 times the natural log of r plus c2. So the temperature profile in 1D radial heat conduction is logarithmic, natural logarithm. So we need two boundary conditions, and they were specified here in the problem statement. We learned that at r equals r1, t equals t1. And at r equal r2, t equals t2. And with those two boundary conditions, we can now solve for C1 and C2. So the other question was about the flux, and that we get from Fourier's law. So here's Fourier's law. Fourier's law of heat conduction also must be written in either Cartesian, cylindrical, or spherical coordinates. And in our case, it's cylindrical. And we've already solved for the temperature profile. It's only a function of r. It's not a function of theta. So this is 0. It's not a function of z. So this is 0. So we just have qr over a equals minus k dt dr. Now, because we've been integrating, we could just go back through our calculation to get the derivative. We could also take the derivative of this, but I want to point out that if we just look one page back up, we have the answer for what dT/dr is. It's C1 over R. So this is equal to minus K times C1 over R. So the flux in 1D steady radial heat transfer goes like 1 over R. And once we apply the boundary conditions to get C1 and C2, we put the C1 in here and we've got the flux. So I'm not going to do those last little bits of algebra, but we have learned that in 1D radial, steady radial heat conduction, temperature profile is logarithmic and the flux goes like 1 over R.